Hello everyone, we'll do today. Uh, this is second lecture in the Relativistic Electrodynamics series. Today we'll do covariant formulation of electrodynamic equations. Electrodynamic equations. Okay. So first of all, I will write three current and three charge density and three current density expressions. So this will be summation in Qn del Q x minus xn t, okay, and your three-dimensional current density is jxt is equal to summation n qn del q x minus xn t and dxn t divided by dt. Okay, right? Where dq, this one, dq x minus xn, this is a three-dimensional Dirac delta function. Okay, yeah, right. Suppose four current density will be what? So we are studying about four current density. So your four current density is what? Four current density will be J alpha xt is equal to summation n qn del q x minus xn t, okay, dx alpha n t divided by d. So this is an expression for four-dimensional current density. Alright. Yeah. We can also write it as J alpha xi t is equal to 0 xi t and j vector xi t. Okay, yeah, and we can also write it covariantly as del alpha j alpha is equal to del rho by del t, yeah, plus delta dot j vector is equal to 0. So this is the covariant form. Okay, all right, yeah. Next, let's move to covariant Lorentz force equation. Next is covariant covariant Lorentz force equation. What is covariant Lorentz force equation? So, what is Lorentz force? Lorentz force is a total electromagnetic force. So, covariant Lorentz force. So, Lorentz force, simple Lorentz force equation is Fl is equal to Q whole into E vector plus 1 by C V cross B vector. So, this is a simply Lorentz force equation. In covariant formalism, we can write, okay, four force. In covariant formalism, we can write the four force. The fourth force can be given as four force can be given as four force can be given as it will be written like this: F alpha L is equal to gamma FL dot V vector divided by C gamma FL vector, okay, which is equal to what? Which is equal to Q by C E dot gamma V vector minus gamma C E vector plus gamma V cross B vector. You must be wondering where this term went here, because see, this is V vector is dot product here. We take the dot product. So dot product of V vector with V cross B will obviously be 0 because A cross B is 0. So this term has vanished from here. Okay. So this can be also written as Q by C E dot U. this can be written as u vector, and u0 e vector plus u cross b. Okay, so u vector is a what? Gamma v vector. Okay? And gamma c can be your u0, your temporal component, right? So this is often referred to as your Lorentz covariant Lorentz force equation. This is covariant Lorentz force equation, okay, which is in compact form. Okay, so if we write it in contracted form, so if alpha L is equal to q by c, if alpha beta, and we have to get alpha here, so beta should be cancelled out. For that, we need to multiply something here u beta. Okay, right. So the components of AF alpha beta. So AF alpha beta is a what? This AF alpha beta is called your electromagnetic field tensor. So electromagnetic field tensor. AF alpha beta is called your electromagnetic field tensor. So what are the terms for it? AF alpha beta. So F00 is 0. All the diagonal elements are 0. F0i is equal to minus Fi0 is equal to minus Ei. Okay. So electric field component EFij is equal to minus of Fji is equal to Levici-beta ijk bk. Alright. What is Levici-beta? Levici-beta ijk is what? If these are in order, like suppose 1, 2, 3, ijk 1, 2, 3, or 2, 3, 1, or 3, 1, 2, then the value will be 1. Okay. And if they are not in order, like 1, 3, 2, or like 2, 1, 3, or 3, 2, 1. If they are not in order, it will be minus 1. If somehow something is equal to something, like I is equal to j, or j is equal to k, or something equal to something, then it will become 0. Okay. So this is your epsilon Levich beta epsilon ijk. Okay. So let's write the matrix for this electromagnetic field tensor. So if alpha beta be equal to minus of f beta alpha, it should be equal to, all the diagonal elements will be first of all 0. So let's write them 0, 0, 0, 0. This is your FC. Okay, I will write it down. F01, F02, F03. This is what? F10, F11, F12, F13, F20, F21, F22, F23. Okay, F30, F31, F32, F33. So the diagonal elements are 0. So F01 will be what? F01 will be F01 should be minus E1, isn't it? So we can write that 0, 0, 0, 0 minus E1 minus E2 minus E3. Okay, and this one will be E1, E2, E3, because this is a negative of negative. Okay, Fi0, this is at F10, na? So Fi0 is minus of F0i. So minus or minus E1. Okay, so this is E1. E1. This one will become what? This one will become minus B3, magnetic field component, which is this Levici beta thing. Okay, yeah. Now, all right, minus B3, and this one will be your what? This will be B2. Yeah, so this will be B3. This one will be minus B2. Sorry, B3, B2, and this one will be B1 minus. So 1, 2, 3. We know what is one. One component is x, second is a y, third component is z. So we can simply put it down there as 0 minus ex minus ey minus ez, and here maybe Ex, Ey, Ez, 0, 0, 0. This will be minus bz. This is by, and this is your minus bx. So this is bx, this is bz, and this will be a minus b1. So this is your what? This is your f alpha beta, which is your electromagnetic field tensor. Okay, this is a tensor of rank 2. Alright, yeah. Okay. Now, now I can. Okay, this is the electromagnetic field tensor, which is used in various places, and it transforms like a rank 2 tensor. Okay, so f alpha beta transforms like a rank 2 tensor. Right. Okay. So this is your electromagnetic field tensor. Next, we'll study covariance of Maxwell's equation. Covariance of Maxwell's equations. Covariance of Maxwell's equations. So, write down in a homogeneous, isotropic, and non-dispersive, non-dispersive medium, Maxwell's equations will be what? What are the Maxwell equations? Del dot E is equal to is equal to 4 pi rho. Next is del cross B minus E by C is equal to 4 pi by C j vector. Okay. Yeah. Next. Next is a what? Next equation is, these are different forms of Maxwell equations. Okay. Del dot B is equal to 0, and the final one is del cross E plus B by C is equal to 0. So there are two equations which don't have any sources. There are two equations which have sources. Okay, rho is your charge density. This is your three current density. All right. Yeah. So if I write them in indexed form, okay, notation, indexed notation. If I write them, Maxwell equations will be del I E I is equal to 4 pi by C J naught, okay, which is your temporal component. Okay, this is the first one. Next is your Levici beta epsilon ijk del j bk is equal plus del naught ei is equal to minus 4 pi by c minus 4 pi by c ji. Okay, third equation del I bi is simply 0. There are no sources here. And final one is epsilon, again epsilon ijk del j ek minus del naught bi is equal to 0. Again, same type of equations. Alright. So the first two equations involve sources, that is like J naught. J naught is your actually C rho, 4 pi rho, C rho, and your JK is actually what? J vector. Okay. K can be 1, 2, 3. So, so first two equations, let me write it again in terms of field tensor. Okay, magnetic field tensor I will write. What it will be? Del I if I0 is equal to 4 pi by C J0. Okay, and the second one will be del I f ik plus del 0 f0k is equal to 4 pi by C 4 pi by C j. Okay, so these are the two equations. Similarly, the last two equations that don't involve any sources can also be expressed. Okay, in terms of these are electromagnetic field tensor. The last two equations, they can be expressed in terms of antisymmetric electromagnetic fields. Okay, antisymmetric, that will be F bar. Alright, so I will write it as del I simply F bar I 0 is equal to 0, and the last one will be del I F bar ik plus del 0 F bar 0k is equal to 0. So here F bar thing is antisymmetric field tensor, EM field tensor, antisymmetric EM field tensor. Alright. So antisymmetric means, if we expand it a bit, so if we write the matrix form F bar alpha beta, so F bar 0, all the again the diagonal components will be 0. So F bar 0 I will be equal to minus F bar I 0, okay, will be equal to minus Bi. Here this is a magnetic field term. Here it was magnetic. Here it was electric field term, but in the antisymmetric part it will be a magnetic field term, right? It would be a magnetic field term. Suppose okay, F bar ij will be what? F bar ij will be minus F bar ji, and this one will be a electric field term with epsilon ijk e k, right? Okay, so let's again write it. I hope you would have understood that one. So you can easily write this one. F bar alpha beta is equal to minus of F bar beta alpha, which equal to 0. All the diagonal elements are 0, 0. And this ones are magnetic field terms. So minus B1, minus B2, minus B3. And this one will be B1, simply plus B1, okay? Plus B1, B2, B3, and these are electric field terms. Here it will be E3 minus E2, and this will be E1, okay, and E minus E3, E2, and this will be minus E1. So again 1, 2, 3 are X, Y, Z. So we can put there, we can put it here 0, 0, 0, 0, and this one will be minus BX, minus BY, minus BZ, BX, BY, BZ. This is your what? EZ minus EY, EX minus EZ, EY, and this is a minus X. Alright? Yeah. So this is an antisymmetric field tensor. So the covariant, these covariant tensors, okay, they can be obtained from respectively from F alpha beta, F bar alpha beta. Suppose F alpha beta I can write as what? Minus F beta alpha, which is your, which is the word I can write as eta alpha mu, eta beta nu. See, mu nu are not here, alpha beta are here, so we have to cancel mu nu. So what will I do? I will write f mu nu. Okay. So which kind of implies that f alpha beta are actually e to minus e transformation and b to minus b transformation, e to plus b, sorry, and this is a f alpha beta. Okay, so this is the transformation. Suppose if we see the other way, the antisymmetric one, so f bar alpha beta equals to minus of f bar beta alpha, okay, which equals to again eta. We will write again mu alpha, okay, or alpha mu, sorry, eta alpha mu, eta beta nu, and again this will be f bar what? F bar mu nu, and it will be upside. We have to cancel this two out. Okay, so we can write here f bar alpha beta can be what? Can be what? E to E and B to minus E, the opposite thing. Okay, B to minus E. Alright, so we'll get f bar alpha beta here, the downside. Okay, right. So using these explicit forms of f alpha beta and f bar alpha beta, we can also verify that f bar alpha beta is also identical with f alpha beta. Okay, so we can say bar alpha beta is kind of identical, is identical with what? with F alpha. Okay, this is a very important point. Yeah, F bar alpha beta can also be written as, there is another thing here. F bar alpha beta can be written as star F alpha beta, which is actually half Levici beta epsilon alpha beta mu nu and F mu. Okay, yeah. F alpha beta can be written as star. No, sorry. F alpha beta can be written as 2 Levici beta alpha beta mu nu. Okay, and F bar mu nu. So this is kind of the transformation again, right? So F bar mu nu we can put here 2 Levici beta alpha beta mu nu star in place of F bar mu star F mu nu. Okay, yeah. So moreover, like the above two Maxwell equations involving the sources, the equations that involve the sources, the LHS contain the three divergence term or time derivative, that is of alpha f alpha beta, can be encoded in a single tensorial equation. Like the first two equations can become a single tensorial equation, and these two can also become a single tensorial equation. So we'll write that. We'll write that. So first two we will write for the first two equations. It will be what? It will be, if I write del alpha f alpha beta will be 4 pi by c j beta. Okay, here j beta is a what? J beta is simply your c rho and j vector. This is the temporal component. This is the three-dimensional spatial coordinate of four current. This is the four current density, right? Yeah. And the second equation can be written as del alpha star f alpha beta should be 0. So these are the two equations which are like the compact form of those four equations. Okay, these two equations are the compact of the first tensorial compact of the first two equations, and the ones which have sources, and this one is the compact form of those two equations which don't have any sources. Okay, so this equation is actually an identity, and it's called Maxwell Maxwell Bianchi identity. I don't know the perfect pronunciation, Bianchi or whatever identity. Okay, so which can also be expressed as a cyclic identity. Suppose if I can write del alpha star f alpha beta is equal to half Levici beta alpha beta mu nu del alpha f mu nu is equal to 0. So I can write it. So this can go out to that side, and it will be like del alpha f mu nu. Okay, f mu nu plus just the exchange of it. It will go to here. It will go here, and this will come here. So del nu f alpha mu is plus, again now it will go here. It will go here, and this one will come here. Del mu f nu alpha is equal to 0. So this is a cyclic identity. Okay, it's a cyclic identity. This is a cyclic identity. Okay, all right. So in absence of sources, we can write a point. Very important point. In absence of sources, in absence of sources, that is rho is equal to 0, j is equal to 0. Okay, the above two Maxwell equations, above two Maxwell's equations are indistinguishable from each other, indistinguishable from each other each other under the transformation, under the transformation. What is the transformation? F alpha beta is F star. So star F alpha beta. This is one transformation, and which is actually, what does it mean? It means E will transform to B and B will transform to minus. Okay. So this is also called. This thing is called, such a transformation is called electromagnetic duality transformation. Electromagnetic duality duality transformation. Okay, transformation. So this is another thing here we have studied. Right? Yeah. So yeah. So these are some stuff that you really need to consider. Okay, covariance of Maxwell equation, electromagnetic field tensor, the antisymmetric electromagnetic field tensor, where there is a swapping of places for magnetic field and the electric field. Okay, four current density, yeah, four force, four velocity, four acceleration, all those things we have studied in the previous class. Okay. So do it slowly. It will take time. Don't be panic that you are not understanding. It's a very tough things to grab, and it will take time. It will take some imagination and self. These are actual self-taught topics. You have to teach yourself, and nobody will explain it to you. You have to understand yourself. Okay. Yeah. All right. That will be it for this class. In the next lecture, we will do. In the next lecture, we will do electro. Next class. Right. Next class, we will do electrodynamic transformations laws, transformations, transformation laws, and and scalar invariance. Okay, scalar invariance, which will include your transformation of electromagnetic fields and like electromagnetic scalar invariance. Then yeah, after that we will move to gauge conditions and potential formulation, all those things. Right? Okay. Yeah. So that'll be it for this class. See you in the next lecture. Any doubts you can tell me in the comment section. Okay.